Temperature is something we use every day, often without even realizing how fundamental it is. It influences our choices and comfort levels constantly, checking the weather, planning our activities around the predicted highs and lows, deciding what to wear, carefully selecting layers to stay comfortable throughout the day, or wondering if our drink will stay cold. We rely on temperature to keep things refreshing. We use scales like Celsius, a system familiar to many around the world, or Fahrenheit, another common way to measure how hot or cold something is, based on the freezing and boiling points of water, benchmarks that define these scales, to describe how hot or cold things feel. It's our intuitive way of gauging thermal energy. But what is temperature really? Is it just a feeling, or is there something more fundamental at play? It's not just a number on a thermometer. There's a deeper physical meaning behind those readings. At its core, temperature measures the average motion of tiny particles, the unseen world in constant flux, atoms and molecules that make up everything around us. These are the building blocks of matter, always in motion. These particles are always moving, jiggling, and bouncing. This constant movement is key to understanding temperature. The faster they move, the more kinetic energy they possess, the higher the temperature. It's a direct relationship between motion and measurement. When you heat water, you're not just making it warmer. You're adding energy, increasing the speed of the water molecules, making the molecules move faster until they turn into steam. It's a visible transformation driven by increased molecular motion. The temperature you read is a reflection of this average kinetic energy. It's a macroscopic measurement of microscopic activity. So, while our everyday scales are useful, they are based on specific substances. Scientists needed a scale based on the true nature of energy and motion, a universal standard. What happens if you keep removing energy, taking away that molecular motion, slowing those particles down as much as possible? Is there a limit to how cold things can get? This question leads us to a deeper, more absolute way of measuring temperature, a scale with a true 0 point. It's the foundation for understanding thermodynamic temperature, a cornerstone of physics, and that's where our journey begins, into the realm of absolute temperature. Let's dive into the world of absolute temperature and explore the Kelvin scale. Temperature, as we understand it, is intrinsically linked to the motion of particles. The faster they move, the higher the temperature. But this raises a fascinating question. If temperature is about particle motion, can we ever make them stop completely? Is it possible to bring molecular movement to a standstill? Imagine cooling something down, pulling out more and more energy, extracting heat, slowing down those energetic particles. As you remove energy, the particles slow, their motion nearly ceases. They become sluggish, reluctant to move. There is a limit, absolute 0, a point where theoretically all particle motion stops. It represents the lowest possible temperature, the ultimate bottom. At absolute 0, particles have the minimum possible energy. They're not entirely still, due to quantum mechanics, but they're as close as they can get. It's not just cold. It's a concept that redefines our understanding of cold. It's the bottom of the temperature scale, a true physical boundary, a point beyond which we cannot go. On the Celsius scale, absolute 0 is 273.15 degrees Celsius, a chilling figure indeed. And if you're using Fahrenheit, it's 459.67 degrees Fahrenheit, equally if not more, bone-chilling. These are far colder than anything on Earth. Even the most frigid reaches of Antarctica don't come close. Scientists have come close, pushing the boundaries of what's possible in low-temperature physics. But reaching absolute 0 is impossible, a goal that remains perpetually out of reach. The laws of thermodynamics prevent it. They act as a fundamental barrier, safeguarding the universe from reaching this ultimate state of cold. Absolute 0 isn't just a number. It's more than just a point on a scale. It's the foundation for a universal way to measure temperature, a cornerstone of scientific measurement. Instead of starting at water's freezing point, an arbitrary point based on a specific substance, what if we started at this true 0, at the point where energy is minimized? That's the idea behind an absolute temperature scale, a scale rooted in the fundamental nature of the universe. It's not tied to any substance, but to the very nature of energy itself. It's a universal reference point. This concept revolutionized science, providing a more fundamental and consistent way to understand temperature, giving us a precise universal standard, allowing for more accurate and comparable measurements across different experiments and fields. Absolute 0 is the bedrock of modern temperature science, the foundation upon which our understanding of heat and cold is built. And it's where the Kelvin scale begins, the absolute temperature scale used by scientists worldwide. When we talk about temperature, we often use scales like Celsius or Fahrenheit. But to truly understand temperature, especially at its most fundamental level, we need a scale that starts at the very bottom, at the point where all molecular motion ceases. That's why scientists created the Kelvin scale. It's a scale designed to measure temperature from absolute zero, the theoretical point at which all atomic motion stops. Named after Lord Kelvin, a brilliant physicist who made significant contributions to thermodynamics, this scale starts at 0 Kelvin, absolute zero. It's the point of no return, the coldest possible temperature in the universe. Because it starts at absolute zero, there are no negative numbers, no confusion. It provides a clear and unambiguous way to express temperature. Each Kelvin is the same size as a degree Celsius, making conversions easy. Just add 273.15 to Celsius. This simple conversion allows scientists to easily switch between the two scales. The freezing point of water is 273.15 K, and the boiling point is 373.15 K. These fixed points provide a reference for understanding the scale. Why does this matter? Because in science, ratios are key. Many scientific laws depend on proportional relationships. On the Kelvin scale, doubling the temperature means doubling the average particle energy. This direct proportionality is fundamental to understanding thermodynamics. This direct relationship is crucial for scientific laws and calculations. It simplifies many equations and makes predictions more accurate. Kelvin is the SI base unit for temperature, used worldwide in science and engineering. It's the standard unit for temperature in almost all scientific fields. It ensures everyone speaks the same language from labs to space probes, whether measuring the temperature of a chemical reaction or the surface of a distant planet. The Kelvin scale connects our everyday experience to the fundamental laws of energy. It provides a link between the macroscopic world and the microscopic behavior of atoms and molecules. It's not just practical, it's essential for accurate universal science. It's the foundation upon which much of our understanding of the physical world is built. Whether measuring a gas or a star, Kelvin is the true measure. It's the scale that reflects the fundamental nature of temperature. It's the foundation for all thermodynamic calculations. Without it, our understanding of energy and its transformations would be incomplete. And it all starts at absolute zero, the ultimate limit of cold, and the starting point for understanding the universe's thermal properties. Just as Kelvin is the absolute version of Celsius, there's an absolute scale for Fahrenheit, the Rankine scale. 0 Rankine is absolute zero, just like 0 Kelvin. The difference? Rankine degrees are the same size as Fahrenheit degrees. This makes Rankine useful for engineers in the US who work with Fahrenheit but need absolute temperatures. To convert Kelvin to Rankine, multiply by 1.8. The freezing point of water is 491.67 degree R. While Kelvin is the global standard, Rankine is a specialized tool for certain engineering fields. Both scales start at absolute zero, just tailored for different measurement systems. Thermodynamic temperature measures the average kinetic energy of particles. But how do we connect energy and temperature precisely? Enter the Boltzmann constant. This tiny number links the microscopic world of atoms to the macroscopic world of temperature. For every 1 Kelvin rise, the average particle energy increases by the Boltzmann constant. For years, the Kelvin was defined by the triple point of water. But in 2019, scientists redefined the Kelvin using the Boltzmann constant itself. Now, temperature is based on a fundamental constant of nature, not a physical substance. This makes the Kelvin scale more precise and universal than ever. It's a leap forward in scientific measurement. The Boltzmann constant is now the key to defining temperature. The idea of absolute zero took centuries to develop. In the 1700s, Guillaume Amontons noticed that cooling a gas lowered its pressure linearly, hinting at a lowest possible temperature. Lord Kelvin formalized the concept in 1848, proposing a scale starting at absolute zero. For over 150 years, the Kelvin scale was tied to the triple point of water, but science aims for definitions based on universal constants. In 2019, after precise measurements, the Kelvin was redefined using the Boltzmann constant. Now, the Kelvin is tied to a fundamental constant, not a substance. It's a modern, robust definition rooted in the laws of physics. Why is an absolute temperature scale so important? The ideal gas law PV = nRT relies on temperature in kelvins. if you double the absolute temperature, you double the pressure, as long as volume stays constant. This direct relationship only works with an absolute scale. Using Celsius or Fahrenheit would break the math. Scientists and engineers use this law daily, from engines to weather models. Even filling a balloon uses the ideal gas law. Kelvin makes the math simple and correct. It strips away arbitrary starting points and reveals the true physics. Thermodynamic temperature is essential for understanding and predicting the behavior of matter. Without Kelvin, science would be far more complicated. It's the key to clear, universal scientific laws. As we approach absolute zero, we enter cryogenics, the science of extreme cold. Here, quantum effects become visible, and the Kelvin scale is essential. Superconductivity occurs when materials lose all electrical resistance at low temperatures, used in MRI machines cooled by liquid helium at 4K. Superfluidity, seen in helium below 2K, allows liquid to flow without friction, even climbing walls. Cryogenics is vital for preserving biological samples, powering rockets, and reducing noise in sensitive detectors. The Kelvin scale is the only way to describe these extreme temperatures. From medicine to space exploration, cryogenics relies on absolute temperature. It opens a window into the quantum world. The cold frontier of science is measured in kelvins, and it's changing our world. Thermodynamic temperature is the universal foundation for measuring heat and energy. Unlike everyday scales, Kelvin starts at absolute zero, tying measurements to the laws of physics. This absolute nature allows for simple, meaningful scientific relationships. Doubling the temperature in kelvins means doubling particle energy. The 2019 redefinition, based on the Boltzmann constant, made the Kelvin even more precise and universal. A Kelvin is the same everywhere, from Earth to deep space. Celsius and Fahrenheit are great for daily life, but Kelvin is the language of science. It connects what we see to the invisible world of atoms. From weather to MRI machines to exploring the cosmos, thermodynamic temperature is essential. It's the king of temperature scales: clear, absolute, and true. Quick comparison. Kelvin and Rankine start at absolute zero. Celsius and Fahrenheit are based on water's properties. Kelvin is the scientific standard. Rankine is used in US engineering. Thermodynamic temperature gives science its clarity and power.